Sets, section 2.1. Set theory is an important branch of mathematics. Here we use what is called naive set theory. Sets are unordered collections of objects. For example, the students in this class form a set. The chairs in this room is another set. The objects in a set are called the elements or members of the set. A set is said to contain its elements. And we have this notation: A is an element A, and this means A is not an element of the set A. Describing a set, roster method. In this method we just list all the elements of the set. For example, S is equal to is the set of elements A, B, C, D. The order is not important. If we change the order, it is the same set. Also, repetitions of elements don't change the set. An element belongs to a set only one time. This notation here means that the set contains the letters A, B, C, D, and so on, Z. It is clear that what is the pattern? This is the set of all letters in the alphabet. Here we have some more examples. V is the set of all vowels in the English alphabet: A, E, I, O, U. O is the set of the integers 1, 3, 5, 7, 9. S is the set of the integers 1, 2, 3, and so on, 99. It is clear that this is the set of all odd integers, positive integers from 1 to 99. And here S is the set of all integers less than 0. It is infinite set, actually. Some important sets: N is the set of all natural numbers, and they are 0, 1, 2, 3, and so on. Z is the set of all integers, natural numbers, and also negative integers. Z plus, positive integers, all natural numbers except for 0, for Z plus. R is the set of all real numbers, R plus the set of all positive real numbers, C the set of all complex numbers, and Q the set of all rational numbers. In set builder notation, we specify the property or properties that all members must have. After this vertical bar, here we describe all properties. So S is the set of elements X such that X is a positive integer less than 100. Actually, after the bar we put a predicate. It may be P of X, and the set builder notation consists of all members, elements X from the domain of the predicate, such that the predicate is true. For example, the set S is the set of integers X such that X is prime. Here we have some more examples of set builder notation. Closed interval is the set of all real numbers X such that A is less than or equal to X, less than or equal to B. And this is an interval closed on the left, open on the right, and so on. Open interval from A to B is the set of real numbers x such that A is less than x, x is less than b. The universal set U is the set containing everything currently under consideration. Sometimes the universal set is implicit, in other cases it is explicitly stated, and the universal set depends on the content, on the context. The empty set is a set with no elements, and we use this symbol or this symbol to denote empty set. In Venn diagrams, the rectangle represents the universal set. In this example, U will be the set of all letters in the English alphabet, and V, this ellipse, it contains all vowels. So it is contained in the universal set. Sets can be elements of sets. For example, in this set we have elements, a set of the numbers 1, 2, 3, the letter A, the set of the letters B and C. In this set, the elements are the integers, the natural numbers, the rational numbers, and the real numbers. The empty set is different from the set with elements, the empty set. Yeah, they should be different. This set doesn't have elements, empty set, and this set has one element. Definition. Two sets are equal if and only if they have the same elements. So, A and B are equal if and only if for any x, x belongs to A if and only if x belongs to B. For example, the set with elements 1, 3, 5 is equal to the set with elements 3, 5, 1, and these two sets are equal because repetitions doesn't matter for sets, and the order of the elements doesn't matter. The set A is a subset of B if and only if every element of A is also an element of B. This notation is used for the case when A is a subset of B. A is a subset of B if and only for every x. If x belongs to A, then x belongs to B, and this proposition is true. It is true for the empty set because the empty set doesn't have elements. So the empty set is a subset of S, and this conditional proposition is always true for any A. So any set S is a subset of itself. To show that the set A is a subset of the set B, we show that if x belongs to A, then x also belongs to B. For example, if A is the set of all computer science majors at your school, and B is the set of all students at your school, then it is clear that A is a subset of B, because every computer science major is also a student in the school. To show that A is not a subset of B, we find an element X in A which is not an element of B. For example, if A is the set of all integers with squares less than 100, and B is the set of all non-negative integers, then A is not a subset of B. Why? Because we can find a number in A, say -1. Yeah, -1 squared is 1, less than 100, so -1 is in A, but -1 is not a non-negative integer, so it is not in B. Another look at the equality of sets. Recall that two sets A and B are equal if and only if for any x, x belongs to A, if and only if x belongs to B. This statement is equivalent to the following statement. For any x, x belongs to A. If x belongs to A, then x belongs to B. And if x belongs to B, then x belongs to A. This way, we see that A is equal to B is equivalent to A is a subset of B. This is this part here. And B is a subset of A. Definition of a proper subset. If A is a subset of B, but A is different from B, then we say that A is a proper subset of B, and this is denoted this way. If A is a proper subset of B, then for any x, if x belongs to A, then x belongs to B, and there is an x in B that is not in A. So this here is extra. In Venn diagrams, this ellipse represents the set A, and it is contained in the set B, represented by this circle, and both are contained in the universal rectangle. The circle is bigger than the ellipse, so A is a proper subset of B. Definition. If there are exactly n distinct elements in S, where n is a non-negative integer, we say the set S is finite. Otherwise, S is infinite. Definition. The cardinality of a set A, denoted this way, is the number of distinct elements in A. For example, the empty set has cardinality 0. Let S be the set of the letters in the English alphabet, then the cardinality of S is 26. The cardinality of the set of the numbers 1, 2, 3 is 3. The cardinality of the set containing only the empty set is 1. The set of integers is infinite. Definition. The set of all subsets of a set A, denoted P of A, is called the power set of A. For example, if A consists of the letters A and B, then P of A consists of this subset, the empty subset, the set A, the set B, and the set AB. Here A has two elements, P of A has 4 elements. And 4 is 2 squared. If we take A to have 3 elements, then P of A will have 8 elements, which is 2 cubed. And we can prove, and we'll prove this later, that if A has n elements, then P of A will have 2 to the n elements. The ordered n tuple A sub 1, A sub 2, and so on, A sub n, is the ordered collection that has A1 as its first element and A2 as its second element, and so on, until An as its last element. Two n tuples are equal if and only if their corresponding elements are equal. Two tuples are called ordered pairs. The ordered pairs A, B, and C, D are equal if and only if A is equal to C and B is equal to D. That is, the corresponding elements are equal. Definition of a Cartesian product. The Cartesian product of two sets A and B, denoted A times B, is the set of all ordered pairs A, B, where A is in A and B is in B. Symbolically, we write this, the set of all ordered pairs such that A is in A and B is in B. For example, if A is the set of the letters A, B, and B is the set of the integers 1, 2, 3, then the Cartesian product of A and B consists of all these pairs. And how many pairs we have? 6. And 6 is 2 times 3. That is, the cardinality of the Cartesian product is equal to the cardinality of A times the cardinality of B. We'll see that this is true always when A and B are finite. Subset R of the Cartesian product A times B is called a relation from the set A to the set B. Different subsets will define different relations from A to B. The Cartesian product of n sets, A1 times A2 times and so on times An, is the set of all n tuples such that the ith entry of the n tuple belongs to the ith set for I from 1 to n. For example, if A is 0, 1, B is 1, 2, and C is 0, 1, 2, then A times B times C consists of all these pairs. How many pairs we have? You can count, how many triples. We have 2 times 2 times 3, 12 pairs. You can count that the number of triples is exactly 12. The truth set of quantifiers. Given a predicate P and domain D, we define the truth set of P to be the set of all elements in D for which P of X is true. That is exactly this set using the set builder notation. For example, if P of X is this predicate, the absolute value of X is equal to 1, then, and the domain is the set of all integers, Then the truth set of P of x consists of the numbers -1 and 1, because only for these two integers the absolute value of x is equal to 1.